The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to our webinar on Prevent Failure Within Your Products and Processes using FMEA. My name is Simon Carlos, one of Wild's Business Development Managers, focusing on training, consultancy and software solutions for reliability engineering, technical safety applications. I'm extremely pleased to introduce Bob Petch, one of our reliability specialists, who will be presenting the webinar today, providing a brief introduction to failure modes and effects analysis, commonly referred to as FMEAs, and how they can be used as a tool to help prevent failures in both product design and the management of processes. The webinar will run for about 25 minutes, and at the end of which we will have a brief Q&A session. I want to make you aware that all attendees are currently on mute, so if you have any questions or comments, please feel free to post them directly onto the questions dialog box during the course of the webinar, and we will aim to address as many as we can at the end of the presentation. Before I hand over to Bob, I wanted to take a couple of minutes to summarise the Wild Analysis portfolio. For the benefit of those who haven't spoken to us before, who aren't familiar with Wild Analysis, we are an engineering analysis business, enabling knowledge transfer through consultancy, training and software. We're the sole UK distributor of the ReliSoft suite of software, which Bob will refer to during the webinar, and in addition, we also have a portfolio of other software products catered to specific industries or physics groups. And I would encourage you to visit our website, wildanalysis.co.uk, and get in touch with us regarding your engineering analysis needs. Now, over to Bob.
Okay, thanks, Simon. Hi, my name is Bob Petch, and in this webinar I'll be giving a brief introduction to failure modes and effects analysis, which we commonly call FMEAs, and how they can be used as a tool to help prevent failures in both product design and the management of processes. The rising demand for more dependable products in tighter timeframes has seen the popularity of FMEAs increase significantly lately. However, there is a good deal of variation across industries and practitioners as to the specific analysis procedures, terminology and also reporting requirements. I will clarify some of the key definitions used in reliability engineering and how these are important for an effective analysis. The true purpose of an FMEA, which is to identify and reduce risks, can often be lost when discussions get sidetracked and the exercise can become unproductive and also frustrating. I will therefore highlight the key steps that need to be covered in an analysis, with emphasis on where focus should be concentrated. To round off the presentation, I will show the benefits of using a dedicated tool such as ReliSoft's XFMEA for performing these analyses in terms of the time-saving features and management tools that ensure as much information is captured as possible. Reliability engineering as a field has the aim of achieving better products through objective assessment. As a result of an effective program, we should be looking to achieve the point shown on the screen, where the goal is to understand previous and current performance so that we can better plan for the future. An FMEA is a fundamental tool in objectively building our understanding of why failures occur and what actions can be taken to improve the performance of products, processes and assets as a result. For simplicity, I will use the word item to describe the subject of any of the FMEAs here, whether that's a system, a component, a product, a process, or an asset, just to list a few. As part of a reliability program, it is important to give a clear definition of what is meant by reliability and also what is classed as a failure. We define reliability as the probability that an item will perform without failure under given conditions for a given period of time. Being a probability, it will have a value between 0 and 1 that will be both a function of time and use conditions. To calculate reliability, it is therefore necessary to have a clear definition of what is classed as failure, as this can be subjective. We define failure as the termination of the ability of an item to perform a required function. The FMEA serves as the first step in outlining what is required in terms of function and what constitutes failure so that the reliability of the item can be analysed and improved objectively. A failure modes and effects analysis is a qualitative technique that is all about understanding and managing risk. Although there are many different types of FMEAs, it's the overall method that is important, with the main steps being, firstly, to identify the ways in which an item could fail to serve its purpose. These are known as failure modes, and this is best achieved by those who understand the item. Next, these failure modes are ranked based on how likely and severe their occurrence will be. This can be incorporated with the detectability of the issue. Finally, based on the findings of the study, actions can be raised to deal with the most critical issues, with less time spent on issues that are of less concern. Although the FMEA is a team activity, it is important that one person is held responsible to ensure that the task is completed on time and to the required level. Furthermore, the FMEA should be treated as a live document, which should be reviewed and updated as the design develops. The purpose of the FMEA is to improve a product or process through objective and critical assessment, and the document should be used to both encourage and track these improvements. Overall, we want to identify the vital few issues from the trivial many in order to use our resources more wisely. There are many benefits of undertaking an FMEA, as when it's done well, it is a proven tool to reduce lifecycle warranty costs, reduce the number of missed improvements during product development, and it's proven to be effective in the identification and resolution of safety critical issues before a potential catastrophe. Any tool that can help identify issues early is invaluable, as it is far less expensive to prevent problems early in product development than it is to fix problems once an item has entered service. Here are some formal definitions as taken from the British Standard 4778, which gives a thorough description as any. An FMEA is defined as the study of the potential failures that might occur in any part of a system to determine the probable effect of each on all parts of the system and on probable operational successes. A failure mode's effects and criticality analysis, commonly called a FMEA, takes this one step further by also ranking the results of the analysis in their order of seriousness. This ranking procedure can be either quantitative or qualitative and is performed on most FMEAs to at least some extent. It is therefore implied that in this presentation, the term FMEA accounts for at least some form of criticality and ranking assessment. There are many types of FMEAs, and it is easy to get caught up on which one is the best approach for a typical analysis, as each one will vary slightly on the viewpoint for what function an item needs to perform. However, all of these types follow a similar structure, with many of these actually following an identical structure. The key differentiator is the point the product's life cycle that is of interest. Where a design FMEA would focus on any issues in design that would hinder the function of a product, such as choosing a battery with dimensions too large for the product package, a supplier quality FMEA would consider the obstacles that may be faced when sourcing the batteries, such as poor spare parts availability that would ultimately lead to increased support costs. The three most distinct types of FMEA can be seen to be system, design, and process FMEAs. It is important to recognise the level that is under consideration, as this will affect what is classified as a failure, effect, and cause. System FMEAs, also known as functional FMEAs, are a form of high-level FMEA that looks at the practical usage of an item and how it will be interacted with, both between individual components, but also with the environment and the end user. The findings of this can then be filtered down to the design-level FMEA for individual components. Here, key issues that would prevent the design from fulfilling the functional requirements of the specification can be highlighted and mitigated. Additionally, the functional requirements may have identified additional requirements that could further develop the design specification. The design FMEA would then be performed based on the assumption that the item is manufactured perfectly, while the process FMEA assumes that the item has been designed perfectly. And so the process FMEA instead looks at any issues that could arise during manufacturing, installation, or operation that would reduce the item's ability to perform its function with time, and is also a measure of quality. An FMEA can be applied at any time of the design cycle, be that during design, development, testing, manufacturing, use, or even decommissioning. The purpose of the analysis is to identify and eliminate potential causes of failure. The earlier the FMEA can be performed, the better. There is a window of opportunity when the FMEA is most effective. Performing the FMEA too early will mean that the required information may not be available, although performing it too late will make it difficult to implement any changes to the item. Shown here is a typical design FMEA as described in the Automotive Industry Action Group Standard. This layout is fairly typical and includes the main headings for many of the metrics that are to be filled out. There should be enough columns to capture the required detail, and conversely, it can be beneficial to remove some of these columns if the spreadsheet is overcrowded or cumbersome. The information entered here is simply representative for a typical design FMEA of an off-road bicycle. The definition of failure mode would be different for someone manufacturing or selling the bicycle than are defined here, which are aimed at the design engineer in helping their decision making. The first column here is for the defined functions of the item. This is the top level of the analysis and is the point at which we outline exactly what we need the item to do. The more specific this description, the more straightforward it will be to decide whether the item fails to meet it. Next is the failure mode. This is the way in which the item fails to serve its required function. There can be many different failure modes for a function, and again, adding specifics such as numerical specifications can help clarify exactly what constitutes a failure. The next main heading here is for the effects. This column captures the potential knock-on effects of a failure occurring. These should be clearly defined ahead of time as to what level in the system these relate to, such as affecting only the performance of the local component all the way up to the end user. This column can be split to capture the effects of varying levels within the system. The causes column here captures the root cause of the issue. This field will contain the fundamental shortfalls that could be encountered. This column will be built by the knowledge around the table, with those most experienced with the item to provide the most insight into the reasons for failure. Next is the controls columns. These are things that can be done that will help both prevent and detect these issues from occurring in service. Finally is the actions column, which are the things that need to be done to mitigate the issues identified in the analysis. These actions can then be assigned to members of the team to ensure that they are completed. There are additional columns on this sheet to capture more detail, such as the mission phase under consideration and also the rankings to determine the priority of the issues, but I'll give a bit more detail on these later. There are many standards outlining the methods, terminology and procedures for FMEAs that have been developed across a range of application in industries over a good number of years. Those shown on screen are a few of the popular ones. However, it's also common for businesses to have their own procedures in place. As I mentioned earlier, although there are many ways in which an FMEA can be performed, it is the thought process and problem-solving activities that are most important. These standards are guidelines for achieving these objectives efficiently, but it can also be beneficial to tailor the process to suit the particular needs of the project and business. Here is the overall methodology, though, for performing an analysis. When we think of FMEAs, it is usually the group meeting that comes to mind, and these are highlighted in red. However, there are many steps that should be performed prior to the meeting to ensure that it runs smoothly and efficiently, as well as afterwards to follow up on the actions that have been defined to ensure that they have been completed and have also been effective in reducing risk. I will now briefly go over each of these components of the analysis in turn. The success of the FMA will depend on the people that are attending the meeting in terms of their level of knowledge of the item, their understanding of the analysis procedure, and also their enthusiasm for the task in hand. The team should comprise people that are knowledgeable about as many different aspects of the item as possible to give varying perspectives on the performance of the item. The best people to do this are not always the most technical. The exercise also helps share information across teams. For example, if an issue that is present on installation of a product has never been relayed back to the design engineers, the FMEA can form the basis of providing this feedback. Additionally, senior management can gain additional awareness of the types of problems encountered by their teams. The size of the team should also be limited, not only to reduce the cost of the activity, but also to maximise the relevance of the discussion. It is often useful to have a third party present to chair and facilitate the meeting. This person does not need to be knowledgeable about the product itself, but should be competent at running the meeting, promoting critical discussion and also limiting any digressive conversation. With the team of the analysis decided, the next step is to lay out the ground rules ahead of the meeting. This is best done by a limited team who are knowledgeable about the FMEA procedure and the needs of the business. By laying out the ground rules and stating the assumptions to be made, the meeting can be focused on the item of interest and the context that it will be considered in. Formalising these rules helps in keeping analyses constant across a business. Using a predefined standard as the basis of the FMEA can also help in making some of these decisions. When preparing for an FMEA meeting, the main steps are firstly, to gather and review the relevant information. This will include information such as drawings, bill of materials, operating environments, and product specifications, so that the FMEA team can decide exactly what the item needs to do and to identify issues with any current implementations. Next, the outputs of the analysis should be defined so that the team not only knows exactly what information is required from them, but also what information is not. This will prevent the team from going into unnecessary detail where it is not needed, and will also help standardise the FMEA practice within the business for consistency. Finally, and crucially, the items that are to be analysed should be identified. As a system will contain many individual components, it's not always practical to assess them all simply on the basis of time and cost. Identifying the most important items, therefore, should take into account the impact on the performance of the overall system. This first step in identifying the critical few from the trivial many can therefore be one of the most important steps in the whole analysis. Similarly, where multiple teams will be performing analyses on the same system, defining which items each team will consider will prevent duplicate analyses being performed. Within the meeting itself, these are the main items of interest that the conversation should centre around. As mentioned briefly earlier, the titles of the columns may change as well as the context with which they relate to, depending on the nature of the item and what stage of development it's under. The overall procedure should cover these main topics. Firstly, to identify the main purpose of the item, which are called the functions. To identify the ways in which the item could fail to perform that function, the failure modes. To determine the effects of failure and to categorise them based on their severity. To determine the root causes of these failures, as well as these are the underlying issues that must be addressed. The controls to both prevent and detect the causes should be created and then actions generated to address them. These can be categorised based on their probability of occurrence and the probability of detecting them. Finally, these can be prioritised by calculating a risk priority number. This will be a product of the severity, occurrence and detection rankings given throughout the analysis. These may not always have equal weighting, and this will need to be tailored to suit the item under consideration. When it comes to minimising the risk associated, there is a point at which the pursuit of completely reliable and safe products and processes is not commercially feasible. We therefore need to decide the point of crossover where the frequency of a failure occurring is compared to the severity of the consequence, and at which point this becomes unacceptable. This is presented with a concept of a LARP, as low as reasonably practicable, whereby extremely severe consequences should have a correspondingly low chance of occurrence, and for events that occur frequently, they should have minimal consequence. This then creates two key domains, an acceptable and an unacceptable or prohibited region, where we can assess whether a particular issue needs mitigating or whether it can be given a lower priority. The actions that will be decided within the FMEA meeting will then fall into four main categories to reduce the risk to an acceptable level. The first way of achieving this is to eliminate the cause of failure from occurring in the first place. This will usually require a redesign at the component level to remove any design flaws, but also may be achieved by reviewing and limiting the application and environmental conditions that the item will be exposed to. Reducing the severity of the failure will allow it to occur more frequently and still be acceptable. This will usually require a redesign, such as adding in redundancy or by adding some fail-safes. Reducing the likelihood of failure will come from reviewing the use conditions of the item. This is again where interaction between different levels in the team can help raise understanding between the issues faced during design, manufacture and installation that can help create a more reliable product. For items where the severity or reliability cannot be practically improved, the ease of which issues can be detected before they become critical will help in reducing risk. This can be achieved by increasing inspection intervals, by adding monitoring systems, or by implementing a closed-loop corrective action system such as ex-fracas to ensure that any issues identified are followed up and rectified. Importantly, the FMEA should be treated as a live document rather than a simple file and forget procedure to tick a reliability box in order for it to be most effective. As the aim of the FMEA is to actually reduce risk, the actions of the FMEA should be followed up and reassessed to ensure that they have been effective. The document should be iterated to reflect updates in the product and as new information about its performance becomes available. The analysis is not intended to shame any individuals or teams for not performing, but instead to identify any opportunities where a team or individual efforts could be most effective and to document where these should be followed up. Most people will already have some experience of FMEAs and will have at least some extent an opinion on the value that they provide to a business. Where these are negative, it is often a result of a bad experience that has been caused by some of the common pitfalls encountered by an analysis. By far the biggest issue is with the level of detail captured. Too much information makes the analysis cumbersome and time-consuming, with participants losing interest and enthusiasm in the process, whereas capturing too little information will mean that the usefulness of the exercise is limited by identifying specific enough failure details for which actions can be raised and assessed. This is helped by ensuring that all participants understand the scope of the exercise, and having a skilled facilitator can actually help on keeping things on track. Most of the other pitfalls can be avoided by thorough planning of the meetings to ensure that ranking criteria and terminology are clearly defined and kept consistent between teams. Here, having one person responsible for the procedure helps by keeping decisions consistent and that the FMEAs are kept up to date and reviewed as needed. There are a number of benefits of using a specific software package to record FMEAs. By using a relational database, existing knowledge can be stored and recalled to either review a previous analysis or to use as the basis for a new analysis on a similar product. This helps both save time and ensure thorough and consistent studies across a business, especially important when different team members and even different teams are involved. Any actions that are raised as a result can also be allocated to those responsible and tracked through to completion. Most importantly, though, it facilitates in making the document live so that it can be kept up to date and referenced when needed during development. ReliaSoft's XFMEA contains many tools in addition to the worksheets for recording the FMEA meetings, such as creating diagrams and system hierarchies to define the interaction between components and subsystems. It has some risk discovery tools to help decide which items should be analysed, as well as then some tracking tools to log, alert team members and follow up on any actions that have been decided upon. The tool itself is also highly customizable to capture the information required for the application. It also contains numerous pre-made templates as defined by various FMEA standards, and these can be edited or new custom templates can be created as desired. I'd just like to briefly mention that XFMEA is just one of the many tools within ReliaSoft's synthesis suite. Reliability results from analyses are stored in a common database that is accessible within all of the programs. This allows the outputs of XFMEA to be tracked and updated as more information becomes available, for example, from lab tests, field tests, and warranty data where it's available. FMEAs also form the basis of maintenance plans, and the output from XFMEA can also be taken and then expanded on in maintenance planning tools such as RCM++, RBI, and MPC. This chart as well just shows how the ReliaSoft tools can be applied throughout the reliability program, from concept right through to support phases. As has been discussed, the FMEA should be a living document that is continually reviewed and updated as more information becomes available. The viewpoint of the FMEA will also change as the design progresses, as it moves into production, installation, and also support. Using a database-driven tool such as XFMEA can help simplify this process, as knowledge of the item can be recalled and updated rather than created from scratch in each instance.
Okay, Bob. Well, thanks very much indeed for that thoroughly enjoyable webinar. Before I open up to Q&A session, I would just like to make you aware of our upcoming webinar on other reliability topics. And on October the 27th, we'll be giving an introduction to ReliaSoft's failure reporting and corrective action system tool, XFracas. And here are two of our upcoming reliability-focused training courses that are held at our Stockport facilities. The Introduction to Reliability Engineering course is usually priced at £450 per delegate. However, for the 14th of October event, we're offering the first delegate from each company attending a discounted price of £99. The ever-popular G400 course, providing a comprehensive overview of core reliability engineering functions and processes, is already filling up, and I would recommend that those wishing to attend to get their bookings in early. Please visit our website, shown on the slide here, to get further information and book your place, and we look forward to seeing you at these events. Thank you for listening. If you have any questions or comments, please feel free to type them into the questions box, and we will try and get through as many as we can in the time we have available. Okay, we already have a few here. So Bob, are you ready?
Yep.
Okay. How many people is best for an FMEA meeting?
Okay. Oh, there's no real hard or fast rules as to how many people should attend an FMEA meeting. In some instances, FMEAs are performed by individuals, so a team of one can be effective. It's desirable, though, to keep the team as small as possible, though, while getting enough different perspectives and knowledge about the item as possible together. Generally, though, it can be difficult with teams above 8 people to keep the conversations on track and to come to a unified decision when moving forward. And so, yeah, generally, the larger the team, the more important it becomes to have some sort of facilitation there.
Okay, thank you. Next question. What kind of person should be in charge of the analyses?
This will really depend on which aspects of the analyses you refer to. In terms of taking ownership of the FMEA analysis procedure, it's quite important, or really quite important, to have someone within the business who is in charge of these. So this will either be a reliability engineer who relays with the other teams within the business, or an engineering manager who has complete ownership of the FMEA procedures, just to make sure that they get completed, they're done on time, and that they're followed up and kept up to date. In terms of the actual meeting itself, though, it's best to either bring in a third-party facilitator to take charge of the analysis, or to nominate a chair within the team to actually lead the meetings and to have almost a final say in any decision making that needs to take place.
Okay, thank you. Third question here. Why would someone use different software other than Excel?
Excel is easily the most commonly used piece of software for recording the results from an FMEA meeting. Similarly, it can also be done with a pen and paper. The main benefit of using a dedicated piece of software is just in the time savings, not only for the creation of the FMEA in the first place and recording it there, but also then when it comes to editing it, adding in new levels to the system can be done nice and easily. Also, expanding and reusing definitions of functions failures can be done not only within the same analysis, but also in any subsequent analyses. So if you're starting out on a new product, you can use an old FMEA as the basis of your new one, which can save a considerable amount of time and also encourage the consistency that's ever so crucial for good FMEAs throughout a business.
Great. Okay. Well, thank you for that. We've got time just for one more, I think. Which standard is best for starting out when setting up an FMEA?
There's a wide range of standards, and a lot of them are very industry specific, and so it would be difficult to recommend one single standard to actually start out from, as this will depend on the nature of the product and the industry. But a particularly useful one is the British standard EN 60812, which was updated in 2006, I believe. Gives a very good overview of the top level of the procedure, much like I've shown in this webinar today, and just highlights some of the decisions that need to be made, gives some guidance on them, and also points towards other standards for more information.
Okay, well, I think we ran out of time now. So can I just say thank you to all those attendees who've attended today. We hope you've found the webinar of interest, and we look forward to hearing from you in due course. Many thanks.
Thanks. Bye-bye.
Bye.